In 11.5, we're going to talk about the common logarithms. The button on the left-hand side of your graphing calculator, the one that says log, is a special type of log. It's the log whose base is 10. We call the log whose base is 10 the common logarithm. So in example 1, evaluate the log of 50,000. All you have to plug into your calculator is log and then 50,000. Hit enter, and the calculator spits out about 4.70 if you round it to the nearest hundredths place. And then in part B, the log of 0.005, you're going to round to negative 2.30. Pretty easy, just shove into your calculator. The common logarithm comes up in a lot of application problems. For example, in example 2, the annual growth rate of the moose population in Wells Gray Park in northern British Columbia, Canada, is 6.7%. This situation can be modeled by the equation n is equal to the log of pt over pi divided by the log of 1.067, where pt is the population of moose today, pi is the initial population of moose, and n is the time in years. A few years ago, the population was 325 moose, and today it's 450 moose. Find the number of years that have elapsed between the initial population and today's population. So the number of years is the log of today's population divided by the initial population divided by the log of 1.067. And you really just need to plug that into your calculator verbatim. And my calculator spits out approximately 5. It's like 5.02. So because it's a number of years, we're just going to call it 5 years. We can evaluate expressions like problem 3 with our graphing calculator's log function. Be careful, however, how you plug this in. Remember, when you call up the log function, a little open parentheses comes in. So one of the things you might want to do to simplify this is maybe just figure out what 3 times 5 cubed is, and then evaluate the log of that value. So now the log of 375 is about 2.57. And then in part B, maybe figure out what 13 cubed divided by 7 is, and then take the log of that, or it's going to be a decimal, so maybe you could just plug in the log of 13 cubed and then divide that by 7. And it's about 2.50, because I get 2.496, which rounds up to 2.50. I've already introduced to you this thing called the base change formula. If you have a graphing calculator that does not have the log base function on it, we can change the log problem to be a common logarithm base in order to plug it into our calculator. So in example 4, in order to evaluate the log base 8 of 172, if you don't have the log base function, you would do the log of 172 divided by the log of 8. And the log of 172 divided by the log of 8 spits out approximately 2.48. In problem 5, it says, refer back to example 2. Example 2 was the one that told us that the population of moose was the log of the population today divided by the initial population all over the log of 1.067. At least that's what I think it was. Let's look back. Yes, 1.067. It says, if the initial population was 325 moose, in how many years will the population triple? Well, they didn't give me the population today, but they want to know how long it'll take for the population to triple. To triple means to multiply by 3. That means that we're going to multiply 325 times 3, and we'll get 975. So we're going to do the log of 975 over 325, and then divide that by the log of 1.067. So the log of 975 over 325 divided by the log of 1.067 is going to spit out about 16.9, which is about 17 years. In problem 6, remember we said that if we have something in exponential form and we don't really know how to find the answer to it, we could rewrite it in log form. Here was the conversion between exponential and log form. So I could rewrite 5 to the 4x equals 73 as the log of base 5 of 73 equals 4x. Well, now I can do this in my calculator, either using log base or using the base change formula. Either way, I'm going to find out that the answer is approximately 2.67. So 2.67 is equal to 4x. Divide by 4, and I'm going to get about 0.67. The last problem, example 7, solve by graphing. This is a nice way of solving any equation that you're not sure how to do the algebra to get to the final answer. This problem can be done algebraically, but the algebra is really nasty. So instead, in my graphing calculator, I'm going to graph 2 raised to the x minus 1 in y1 equals, and I'm going to graph 5 raised to the x minus 2 in y2 equals, and we're going to find where those two sides of the graph intersect. And that value of x is going to be the solution to the problem. So 2 raised to the x minus 1 in y1 equals 5 raised to the x minus 2 in y2 equals. Here's what the graph looks like. You can see where it intersects, and then all you have to do is second trace number 5, and then hit enter 3 times. Second trace 5, enter, 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 and it tells me the answer is approximately 2.76. And that was Common Logarithms.